Suppose you were working with the following scenario. 10 girls of various heights and ages are selected from Piedmont schools. One of these 10 will be selected at random, and you will be asked to predict her height. The error, also known as residual, will be recorded. Suppose this process, randomly selecting one girl from the group of 10, predicting her height, and recording the error, is repeated a few hundred times. You want your predictions to have the lowest possible total squared error. What should be your method of prediction? Okay, so you kind of got this idea where you want to make predictions, and this is what regression is all about. Regression helps us make predictions. So what I've set up here is I have a spreadsheet where I've listed the 10 girls who were randomly selected, and you see here are their ages and here are their heights. And you want to design a guessing model that if you were to pick one of these 10 girls at random and you had to make a good guess at her height, what should you do? So I've got here a few different models, and hopefully this will help you understand what we mean by the coefficient of determination and different models. So here we go. So one way to proceed is you could say, well, you know what? In order for me to guess at their height, I would like to know what the 10 individual heights are. I'm not going to worry about the ages, so I'm going to kind of ignore the ages. What I'm going to do is see if I can kind of white these out here, if it'll let me. Okay, so let's say, okay, you just ignore the ages. You're not worried about how old they are. You're simply focused on how tall each one is. And you could say, all right, I'm going to take the 10 and I'm going to figure out the group average, which is 55.3. And so that's what I'm going to use. Every single prediction, anytime a girl is chosen at random, I'm going to predict 55.3. And I'm going to do that all the way for any of the 10. I'm not really worried about how tall she is. Let me see if I can kind of fill this down a little quicker. There we go. So we're just going to guess 55.3 all the time. So each of those guesses is going to have a certain amount of residual, a certain amount of error. There'll be some negative errors and some positive errors. And then here's all the squared residuals. And you end up getting a total squared error of 428.1. That's a lot of squared error. And so over here, I've kind of drawn the line. This is the line y equals 55.3. And you can kind of see these gaps here are the residuals. And I've also provided a residual plot of what happens if we use this line as like kind of the line of best fit. And so we have a lot of error here. And we also have a residual plot that doesn't really show randomness. It's kind of you've got a whole bunch of points below, and then you've got a whole bunch of points above. It's not really a random scatter. So this is not a great model. The residual plot says this model's not really very good. And you also look at the squared error is huge. It's like 428.1. This is probably the worst way to do the problem of just like ignore the ages, don't use the ages at all, and just rely solely on the heights. Now we happen to call this is what we call SST, for sum of squares total. It's the total amount of error. It's the total amount of variation that you see among the heights relative to the group average. And so I'm going to kind of bold that in if I can. So that's SST, sum of squared total. It's what happens when you kind of just use the y average as the predictor. It's kind of the worst way to go here. And it turns out you have the coefficient of determination is 0. In other words, knowing their ages is going to have no effect on guessing their heights. And that's not a surprise because you're pretty much ignoring the ages. So let's go ahead and scroll down to the next one. This is the one you're probably most comfortable using, which is we call lines of best fit. So what I have over here is in the second case is now let's say I use the ages and the heights that I know about, and let's use those to build a line of best fit. So I put these into the applet. It graphed all the points for me, and it drew a line of best fit, and it gave me this equation right here. This is the equation for the line of best fit. And you can see, yeah, that line seems to fit the data pretty well. And so this is looking pretty good. Definitely much better than the first case where all you were using was the y-average. And so when you do the analysis, you end up getting a squared residual of 17.4, much better than the 428.1 that we had earlier when we're just using the averages. And so what you have is, of this 428.1, which is kind of like the total error that's possible, the total squared error, we've been able to eliminate a lot of that error, okay, and to where now we only have a much smaller SSE of 17.4. So if we take the total, which was 428.1, and then we subtract what's left over, 17.4, we realize that, okay, we've been able to kind of eliminate 410.7 in terms of squared error. In other words, this model that we've used here is kind of explaining or accounting for 410.7 of the 428.1 total error. So that if we do this calculation of 410.7, that's the error that's been kind of eliminated by our line of best fit, and we divide it by the 428.1, which is the total amount of error, we end up getting a really high coefficient of determination. So the point of this is to kind of tell you that, okay, if you look at the total error, and then you look at the error that's left after you've done line of best fit, and you start to say, well, how much of the error have I eliminated? I've eliminated about 410. I've eliminated about 95.9% of the error. And that's what we mean to say, oh, okay, so this line, this model right here, okay, which is based upon ages, okay, is explaining about 95.9% of the variability. Here's the variability that we're seeing in the y variable. Here's the variability that we're seeing in the height. And this model's been able to account for or explain about 95.9% of that, which is a very, very good coefficient of determination. Now, it turns out if we took the correlation and squared it, okay, we would also get the coefficient of determination. But this only works in the case where you're doing linear regression. Now, before we go on, let's also take a look at the residual plot for this linear regression. Here's the residual plot. And here we see curvature. In other words, for the younger girls, like the 5 and the 6-year-old girl, we have a model that's over predicting their height. And then when we go from about ages 7 up through, I'm guessing about 14, we see that our model is actually under predicting the heights. And then when we get to the 16-year-old, once again, we see that we're over predicting. We call this curvature, where we're kind of like, we've got some points below, then we have a whole group of points that are all above, and then another one below. So that's kind of telling us that using a line as sort of the model of best fit, okay, is probably not the best way to go. There's still curvature here. We want to see sort of random scatter above and below, and that's telling us that our model is a good model. So even though we have a really high coefficient of determination, right, this model we've chosen is explaining like almost 96% of the variability that we see in heights. This is kind of telling us, there's a better shape out there. There's something better than a line if we want to basically make the best prediction possible. In other words, we want to have the lowest amount of squared error. So let's take us down to the third model. And this is something you don't do too much of in first-year statistics, okay? But rather than doing linear regression, we start to talk about curved regression. We start to use different curves of best fit. Now, what I've chosen here is I've chosen what's called a power model, which is basically you take some power of x and then usually have a multiplier out front. We call it ax to the b power. You might have learned about power functions in a previous math class. So that's what I used here. I used a power model instead of a linear model. And this is what the spreadsheet came up with, is it drew a line like this, which looks like it's a really good fit. And I went through and did the analysis, and look at that. We're down to an SSE of 4.718. We've been able to reduce the amount of total error. Remember, at the beginning of all this, the total error was 428.1. And we've been able to get that down to a 4.718. Even better than the 17.4, which we had with the linear model. So let's see what the coefficient of determination is. Now here, because it's a curved model, this correlation number, which is a measure of sort of linear association, we really can't use that here. We have to go back to the kind of the more basic idea for coefficient of determination. We start with the total amount of errors. So there was 428.1. That was the original. And then we look at how much error remains after doing this sort of we call power regression. And we're at 4.718. So this model has been able to eliminate or explain 423.382 in terms of the squared error. So if we were to kind of say, all right, we're explaining, let's take the 423.382 and let's divide it by the 428.1 total error. Wow, look at that. The coefficient of determination is now up to 0.989. This model right here, okay, is explaining about like almost 99% of the variation. This variation that we see in heights right here, okay, can be explained or covered by this model. This is a great model. It's certainly the best of the three that we've looked at in this video. Over here, I've also generated the residual plot. And this one it's a bit better. It still might have a bit of curvature. I'll see I've got 2 points below, 1 above, 1 below, 3 above, 1 below, above. So this one at least has a little more randomness of scatter. Hard to say if there's curvature here. There's so few points. But I would certainly investigate some other curves that I know about, like maybe a quadratic equation, maybe some kind of exponential or logarithmic equation. A lot of this depends upon your experience with different function types and what you might try. Desmos is actually a great tool for kind of trying different curves, and we'll talk about that later this week in class, how to use Desmos to build these kind of curved regression models. So I would maybe look at that. So the big takeaway though here is the coefficient of determination. The way you can kind of figure that out is ask yourself, well, what's the total amount of error? And that's just by looking at the average alone, using just the average to make predictions in the y variable. That explains what's called total error. And then start to say, well, let's start using other models rather than just let's use the age as a predictor here. Let's not ignore it. Let's use the age and use that to predict the height. And so we have a linear model here, which does a great job of accounting for a lot of the variation. Then when I went to a curved model, I was able to explain even more of the variation. So hopefully this gives you a little more information or insight on the coefficient of determination and how we calculate it. Thanks for watching.